Okay, welcome once again to the study. And I noticed that my video on, hang on for a second here. I noticed that my video on line integrals did not, it has some problems on YouTube. So I'm going to give an abbreviated version of that again so you've got something. And I want to add something to it. So we're going to take a vector field. That is, we're going to take a function that maps R2 to R2. And so f of x and y has two components, p of x and y and q of x and y. This is standard notation. And each one of these is a real valued function. We're also given a curve in some way, and I'm going to give it in the parameterized form. That's what we'll be using anyway. So say the interval 0, 1 into r squared. And we want to look at something called line integrals. We're thinking of F as a force, like a wind, and we want the force that's with you on the curve alpha as t goes from from 0 to 1. And this will be an integral. And we want the force that's across the path. So force that's with you, force that's across the path, and we're going to integrate both of these. Now, force is a vector, and that's given by this vector field. Force that's with you will just be a number because it will be force that's in a tangential direction. And the same thing, force that's across you. So now I'm going to draw a picture and we'll do some of this. Maybe over here we'll do width. Here's our curve C, and it's oriented by the 0, 1. So this is the beginning, this is the end. Here's a cross. Again, we have the same curve C. It is oriented. And at each point of the curve, we have a vector field. And let's say that vector field is like this at any point. For the force that's with you, we want to know the component of the force in the tangential direction. So I'm going to put a T here, and we want to know what it is in the normal direction. So we'll put an N here. In this case, it will be negative because it's got a component in the opposite direction. And these are unit vectors. And so the force that's with you at, this will be a point alpha of t, the force that's with you will be F of alpha of t. That's this blue vector. That's the force, but the ones that with you is dot t, dot that tangential vector. And over here, the force that's with you, F of alpha of t, dot product with n. Now these are not vector quantities, these are just scalar quantities. And so we will integrate those. Pictorially here, it is the projection of the force in the tangential direction. So it's just a dot product with a unit vector. Same thing over here, but it will be negative. So it'll be that length, but it'll be a negative value. And these are the two integrals that we're going to do. We're going to integrate this and integrate this on C. So let's do one at a time. So let's do the width first. So the integral from t equals 0 to 1, that's because of alpha. F of alpha of t dot alpha prime of t divided by the length of alpha prime of t, that's the tangent vector. We will need an expansion contraction factor due to alpha, expansion contraction factor because of alpha dt. And to find the expansion contraction factor due to the parameterization, this will be equal to, now this is not a determinant now because alpha prime of t, if it's in 3 space, will be x prime of t, y prime of t, z prime of t. And so the expansion contraction factor is the square root of the sum of the squares of the largest square determinants. Well, they're 1 by 1. So this will be x prime squared plus y prime squared plus z prime squared, z prime of t squared. So that's the speed. And that's what we integrated to get the length before. That is the expansion contraction factor due to parameterizing the curve. So this is the speed. Which is the length of alpha prime of t. And the key here is that you get this cancellation. So integrating the force that's with you amounts to integrating between 0 and 1 f of alpha of t dot alpha prime of t dt. Now, if no parameterization is given, this is called pdx plus q dy. P and q are the components of f, so f has 2. This is a dot product here, pq dot dx dy. So this indicates the derivative term over c. Now these are equal. If you have a parameterization, this becomes this. So this is it for the force that's with you. For the force that's across you, it's a little different, but not that much. We again have C, it's again oriented. And I'll again assume that alpha is the parameterization. We've got a force at every point. We look at a normal vector. Now, if we're in the plane, then this normal vector is easy to get, and there are 2 options. If you have any vector AB, then to get normals, you could take B minus A, or you could take minus BA. So in 2 space, it's easy to get normals. We'll also do something like this in 3 space, but in 2 space, it's easy to get normals. It's one of these 2, there's a choice. And these are kind of the left-hand, right-hand rule. So in the plane now, if we use the left hand and the hand itself, these fingers point in the direction that the curve is oriented, then the thumb will give this normal. This is the left-hand rule. The right-hand rule, the thumb would give what is out. We'll use the left-hand rule, which means that we do this one. So this is the left-hand normal, but we'll do the same thing. We'll integrate 0 to 1, the force of alpha of t, but this time we'll take a dot product with n. This is kind of an intermediate step. f of alpha of t, and now we have to find n. Well, here we had alpha prime of t, maybe alpha prime of t is x prime of t, y prime of t. And so alpha prime perp of t is minus y prime of t, x prime of t, where the perp means perpendicular. And so n then is equal to minus y prime of t, x prime of t, divided by the length of this, which is minus y prime squared plus x prime squared. And we still need the expansion contraction factor, dt. And the expansion contraction factor is due to the parameterization, not due to the choice of n. So the parameterization factor is this again. The speed, but notice that the speed, which is in the numerator, is the same as the length of how we computed this denominator. So this integral becomes the integral 0 to 1 f of alpha of t dot minus y prime of t, x prime of t, dt. So this is it. But there's a little bit more here. This is the integral of PQ, this time dot product with minus y prime, so minus dy dx over c. This is meant to be obvious that it's equal to, and that you need to parameterize c to make use of these things. So this is minus p dy plus q dx. And so this is equal to minus pq. Maybe we do it the other way. Q minus p dot dx dy. Putting these in the order that they came. So q dx minus p dy. This is the same thing. And so over c. So this amounts to integrating a different vector field, not pq, but q minus p, and doing the force that's with you across a different vector field. So I wanted to point that out because the line integral of f, let's do it this way. The limit f dot d alpha along c is equal to the integral of p dx plus q dy on c. This is the force that's with you. The force that's against you is this integral here, q dx minus p dy on c. This is the force that's against you. And we could look at it this way, that if you define f perp to be equal to the q minus p force field, so this is a different force field from f, then this is the same thing as, this one is the same thing as integrating f perp. along C, d alpha. So integrating f d dot d alpha along C, this is the regular line integral, the force that's with you, is equal, and that's this one, but this is the force that's with you along alpha, but the force is F perp. And if you integrate F perp this way, then you get the force that's across you. So either way, but this is a good way to look at it, that every force comes with a perp force. And if you integrate them both, then one of them gives you the force that's with you, one of them gives you the force that's across you. So this was actually what I did last time. What I'd like to talk about this time is a method for computing these. It's called the fundamental theorem of line integrals. And this is the idea that if we begin with a vector field, mapping from R2 to R2, this is potentially a derivative. So, and it was potentially a derivative of a real valued function. Because the derivatives of real valued functions are of this form. Let's just do one just to check. Suppose we take a real valued function like temperature, given by this equation, f of x and y equals x squared y minus 3y squared x plus y. And we take the derivative of this guy. So that consists of the derivative with respect to x, 2xy minus 3y squared, comma, the derivative with respect to y, x squared minus 6x plus 1. And lo and behold, f prime is this type. It takes ordered pairs, points from the plane, and it maps it to ordered pairs. Now, so this is an important thing to notice here, that these vector fields are potential derivatives. Now, I said potential because they don't have to be a derivative. Looking at a little one-dimensional calculus, if you take any continuous function, f, you may not be able to differentiate it. Some functions you can't differentiate even at one point, even though this is continuous. But you can always integrate it. So this is going backwards up the line. You can always do this. This always checks out. If you begin with a continuous function, you can always back it up. So that if f is a real valued function, you can always integrate it. If you integrate it, you get a continuous function. So you can always integrate that. And the process going the other direction is the integral, antiderivative process. And that's the fundamental theorem of calculus. It tells you that these antiderivatives, among other things, they exist. So you can always go up, but you can't necessarily go down. In higher dimensions, you can't necessarily go either direction. So even though this is continuous, it might not be a derivative of anything. And it's easy to find such examples. If you take, let's say, x, y, and 0, what would be an antiderivative of this? Well, this would be that if there was such an f of x and y, then this would be f sub x down here. So if you integrate this with respect to x, you're going to get a piece of this. So this would be x squared over 2y plus some other stuff. But this definitely has to be there in order that when you take the derivative with respect to x, you get this. But if you take the derivative of this with respect to y, you get x squared over 2, you don't get 0. So any antiderivative of this function, this vector field, would have to include an x squared over 2y term. But if it includes this term, it can't be 0 for the derivative with respect to y. So not every continuous function has an antiderivative, but some do. And the fundamental theorem of line integrals says the following, that if f mapping R2 into R2 is the derivative of a function capital F from R to R, then let's put and C is any curve from point A, call it A1, A2, to point B, B1, B2, then the integral along the curve from A to B, this oriented curve, of the vector field PDX plus QDY equals the antiderivative evaluated at B minus the antiderivative evaluated at A. So that's the bottom line that appeared as the top line. So this is just like the fundamental theorem of calculus. If you can find an antiderivative, then no matter what the curve is, you're going to get this for the line integral of that vector field. You're going to get f of b minus f of a. So when you're doing line integrals, one of the first things to check is it a derivative? Getting long here, but so the process of finding line integrals begins here. Is little f a derivative? If it is, then the answer is easy using this fundamental theorem of line integrals. Find the antiderivative, plug in the endpoints, subtract, amen. So yes, then you use the fundamental theorem of line integrals, and you're done. If it's not a derivative, then parameterize C and plug and chug. So the process of finding line integrals, you'll be given a C, you'll be given a vector field to integrate either across or along it. If the vector field that you're working with is, if little f is a derivative, if your vector field is a derivative, then find the antiderivative, sub in the endpoints, you're done. If not, then you have to parameterize C and actually handle that integration. And there are some words from this that come from physics. I used words here that came from math. But functions that have derivatives are called conservative. This says f is conservative. Conservation of energy, conservation of mass. Every time in physics you hear the word conservative, it means is a derivative. You hear politician is conservative. It has absolutely nothing to do with being a derivative. All right, but conservation and conservative in physics always means that the vector field you're dealing with is a derivative. There's an antiderivative of it. And that antiderivative which in math we call primitive, a primitive, for it. So anyway, these antiderivatives also have names. And right now, the antiderivative of a conservative vector field is called a potential function. So in physics calls this potential function. So if you're given a conservative vector field, it has a potential function, meaning an antiderivative. Okay, so in a nutshell, this was it. And I'm going to cut this off. I'll give you some homework to look at where you actually find some of these. And hopefully I'll post this later this afternoon. Thanks a lot. See you tomorrow.